Hello everyone, my name is Mikolaj Piorczynski. This summer I had the opportunity to work at the Atom Lab under the supervision of Rachel Lee, Abby Turner and Professor Artur Dubrawski. Today I'm excited to present my work on model merging perspective on personalized federated learning. The project was completed as a part of the Robotics Institute's Summer Scholars program. Let me start by introducing the problem that federated learning aims to solve. Let's imagine a scenario where multiple clients, such as hospitals or financial institutions, want to collaboratively train a machine learning model without sharing their raw data, which may contain personal or confidential information. In such cases, traditional machine learning approaches that require collecting all the data in a single data center are not feasible. This is where federated learning comes into play. In federated learning, clients train models locally on their own data, sharing only model updates, not the data with a central server. The server aggregates these updates to create a global model, which is then sent back to the clients as an initialization for the next round of local training. This process repeats over multiple runs until convergence, enabling collaborative learning without compromising data privacy. In practice, however, clients often possess data with varying distributions or even entirely different tasks, a challenge known as data or task heterogeneity. In such cases, a single global model may fail to meet the needs of all participants. Personalized federated learning, or PFL in short, addresses this limitation by enabling each client to maintain a personalized model tailored to its unique data and task, rather than relying solely on one shared model. In this setup, the global modeler serves more as a starting point for each client's local fine-tuning, rather than a one-size-fits-all solution. However, the aggregation step can be particularly challenging under task heterogeneity due to differing objectives and data distributions across clients. In my work, I focus on this aggregation stage, combining local models into a global model in a way that supports personalization while also mitigating conflicts between clients' updates. Recently, there has been growing interest in machine learning community around the model merging. The goal of model merging is to create a single multitask model by combining multiple models fine-tuned on different tasks starting from the same pre-trained checkpoint without any additional fine-tuning. Motivated by the phenomenon of linear mode connectivity, this is achieved by aggregating model parameters. A major challenge in model merging is task interference, meaning that tasks can negatively impact each other's performance when their updates are combined. We observed a strong similarity between these two fields, model merging and personalized federated learning. In both settings, multiple clients fine-tune the same pre-trained model on different tasks, and their updates must be combined into a single model. Motivated by this connection, we aim to bridge the gap between these two fields, and in this work, we explored the use of model merging techniques within the federated learning loop. We also ask a question if a better multitask global model can more effectively guide each client's local training. We conduct our experiments on a subset of 10 natural language generation tasks from the supernatural instructions dataset. It includes a diverse set of tasks such as text classification, summarization, and question answering, perfectly simulating a task heterogeneous setup. We fine-tuned the Llama 3.21b model using LoRa adapters, which is a common technique that enables efficient fine-tuning of large models. For evaluation, we report the RUCH-L score, which is a standard metric for text generation tasks. In our experiments, we evaluate three merging strategies. Task arithmetic, which is in our case simple federated averaging baseline. Ties merging, a more sophisticated approach that first removes parameters with the smallest magnitudes, then determines each parameter's sign based on the majority of the models, and finally averages only those parameters whose signs match the majority. And the third one, iso-C merging, an approach that flattens the singular spectrum of average model to reduce dominant directions that could cause interference between tasks, and also improves the alignment between task-specific models and the merged model. Since we work with LoRa adapters, we explored different ways to merge the LoRa A and B matrices, which we call merging space. We experiment with merging the A and B matrices independently, merging full-size update matrices obtained by multiplying the A and B matrices, and finally merging in node space, a method designed specifically for LoRa adapters. It first projects the full-size update matrices into a shared space for merging, and then reconstructs the merged full-size updates from that space. For merging spaces that produces full-size updates, we tested two strategies to recover low-rank adapters for the next training round, specifically TSVD, which provides the optimal low-rank approximation, and also merging the full-size update metrics into the model backbone and reinitializing LoRa parameters for each client. Okay, so let's talk about the results now. In the table below, we present the aggregated performance across client tasks for tested merging strategies. As we can observe, the best performing configuration is the combination of iso-C merging in node space with the TSVD client initialization. And the second best is also iso-C, but applied in the full space with LoRa adapters initialization. Interestingly, the simple federated averaging, so here task arithmetic with A and B space, yields also competitive performance, remaining a strong baseline. We can also observe that ties merging underperforms across all configurations, what may suggest that not fully converged models may not contain redundant parameters that this method tries to exploit. For the best combination of merging strategies, we analyze the client's performance along the training trajectory. Similarly, we also do the same for the global model obtained in each communication round across client tasks. We present results in the pictures below. Interestingly, for the best combination, we observe significantly faster convergence of client models without the improvement of the global model performance over the simple federated averaging. We can see that in the first few rounds, obtained global model is significantly better than simple federated averaging, but after these few rounds it plateaus. The reason of this behavior remains unclear for us now and requires further investigation. Okay, so to sum up, in our project we explored the connections between personalized federated learning and model merging. We showed that improved parameter aggregation methods can boost PFL performance. Additionally, we found that in PFL, a better global model doesn't always lead to better personalized models, and stronger client model performance doesn't always mean the global model is better. Okay, that's it. Thank you for your attention.